Hello, everyone. My name is Chris Down. I work as a kernel engineer at Meta. I mostly work on the kernel's memory management subsystem. Especially, I'm a contributor to, as you would imagine, cgroups, because, this is the main thing we're going to be talking about today. I'm also a maintainer of the systemd project, so that's two things in about 2 sentences, which you can hate me for. And most of the time, my job is basically thinking about how we can make Linux a little bit more reliable, a little bit more usable at scale, a little bit more nice. Oh, lovely. The ambiance is impeccable in here. We have 1 million plus machines at Facebook. We can't just buy more RAM. We can't just kind of wing it. We need to make the absolute maximum of every single machine that we have on the fleet, otherwise it adds up to like a really large deficit. My hope is by the end of this talk, you'll be able to understand how to use cgroups and some of the other resource control primitives which we've been inventing to protect against outages and performance problems. You hopefully will have like an actually usable way to, the ambience is changing all the time. The mood, I feel like it changes depending on what I say, so I'm gonna be very careful what I say to keep the lights on at this point. Hopefully you'll have some new tools in your arsenal to use when debugging or support when you need to apportion services across your fleet. And even if you don't have millions of machines, this is still something that's quite relevant to you. Maybe you are more capable of, yes, of shoving hardware at the problem, but you still have to account for and properly apportion services, right? This can't just be done by looking at RSS or IOTOP or things like that. It's expensive to get this wrong, like either in cost of money or in terms of outages and incidents. So that's the kind of topic I want to talk to you about today. However, the last 7 years we have increased Meta's reliability and capacity, and how these improvements might be relevant to your needs in your organization and your situation in production. At Meta and in the wider industry, we are increasingly finding that we cannot effectively solve scaling problems just by throwing hardware at the problem. We can't construct data centers fast enough. We also have agreements about clean power. We can't source clean power fast enough. And we have millions and millions of machines, and we just cannot afford to waste capacity. Ultimately, we need to make more efficient use of resources, and we need to build the kernel infrastructure which allows us to do that. Another challenge that we have is that many huge site incidents are caused by lacking resource control. Not being able to readily control things like CPU, I/O memory, this kind of shared states across a machine, is one of the most pervasive causes of outages and incidents in the industry at large. And we need to sustain an initiative industry-wide to solve this problem. The elephant in the room, of course, over the last 3 years is COVID. I'm aware that this slide means nothing to you if you're all American, but this was my government's shambolic template for all COVID things. So cultural relevance there for you. This is a little bit of cultural relevance. So changes in behavior due to COVID dramatically increased the usage of Facebook as a platform. This was by about 27% over what was projected. And this also came at a point where, amusingly, we also couldn't just buy more memory, more CPUs, because there was a shortage, right? There were shortages due to COVID. So what we really needed was a way to make more efficient use of the existing hardware that we already had across the fleet. And this led to a fairly significant acceleration of our existing efforts around resource control and efficiency. Now, every time I give a talk like this around memory or something like this, I always end up with some Hacker News commenter. I think we know the kind of Hacker News commenter that I'm talking about. We always end up with some Hacker News commenter who says, why can't you just buy some more memory? Now, I don't know how trivial people in this room think that is when you have several million servers, but it turns out it's actually kind of complicated. There's a huge amount of cost involved there, not just in money, which is indeed substantial, and I'm very grateful that it's not coming out of my bank account, but also in things like power draw, in things like design thermals and hardware design trade-offs. Not to mention during COVID, like I said, you just can't even get those things anyway. They're all so scarce. So how does all this talk about capacity and reliability relate to this cgroups thing mentioned in the title? So cgroups are a kernel mechanism by which you can isolate and control things like memory, CPU, I/O, resources which you share across processors on a machine. I'm sure if you've operated containers before, you've probably seen the name in passing. Every single modern container runtime, Docker, CoreOS, Kubernetes, you name it, uses cgroups under the hood. And there's a reason for that. Cgroups solve a lot of the long-standing problems that we have with classic Unix resource control, like ulimit and the like. A lot of the technologies that I'm going to be talking about today are pretty recent, to be honest. Is a brief timeline of like the last kind of 20 years of the resource control space, and as you might notice, resource control has become more and more important and accelerated in timeline in recent years as we reach the limits of capacity. So we needed to build the appropriate technologies in order to mitigate that and do things like complex stacking and resource isolation in prod. There's also a reason here, like there's an implication here that running a really old kernel, which is what a lot of people do to quote-unquote remain stable, is not a really very good way to maintain a fleet, right? There's a reason why companies like Meta and Google and the like typically run the latest kernel in production or something very close to it. Because if you want the tools to tackle issues, running a 2 or 3 or 4 year old kernel doesn't really cut the mustard, especially if you are, a forward-thinking place using the latest technologies. You want to use something like eBPF, you want to use the latest in containerization technologies. It doesn't really manifest very well. Even if you're just a downstream user of, containerization technologies like Kubernetes or Docker or systemd nspawn, just running with an old kernel means there's a lot of things which cannot be isolated, a lot of things which cannot be protected from. Just as one example, if you run a kernel before 5.8, you have a drastically less efficient and drastically less useful swap algorithm, which we'll be going over a little bit in this talk. You're also missing a huge number of the containerization improvements, which you get for free, even if you just continue running systemd or continue running Docker or Kubernetes. So running an old kernel is not really an option in such a rapidly developed space as this. So this is all very well and good, but usually, you don't usually, like I said, you may just see cgroups in passing. You don't usually do anything with them, right? So for most services on your machine, you probably use cgroups only through your service manager, like systemd, or your containerization platform, like Docker or Kubernetes or whatever. So most distributions boot with cgroup v1 enabled rather than cgroup v2. So these container managers, while they support v2, will only use v1 because it's decided at boot time. So the problem there is that there are many things which you simply cannot do in cgroup v1. So we'll be talking about that a little bit, but the isolation semantics, even if you use exactly the same configuration knobs on these things, tend to do something completely different in v1 and usually not the right thing. So it could easily be exposing you to these kind of resource events which cause site incidents or lack of efficiency which you could be avoiding if you're using cgroup v2. Cgroups have existed for about 14 years now, and they have changed a lot in that time, most notably 7 years ago in kernel 4.5. Doesn't feel that long ago that we released kernel 4.5, but it really was 7 years ago, and we released cgroup v2 in that. I gave a whole talk at the time on why we are moving to cgroup 2, but if you're interested in a lot of detail about why, I will briefly cover it now, but there is a whole talk, a whole kind of hour-long talk available at the link below, and it goes over kind of what our thoughts were at the time that we released it. The first major change is in how we organize the cgroups themselves, right? So this is actually a very technically complex change. It might look initially like an aesthetic change, but moving to a totally different API has allowed us to do things which we weren't able to do technically before. If you've had some interaction with cgroups in the past, it's entirely possible, and quite likely you have been using this, which is cgroup v1. In cgroup v1, sysfs cgroup contains controller names. At the top level, that's something like memory or CPU or PIDs. So in these directories are hierarchies for each resource. So for example, the PID cgroup hierarchy has something to manage PIDs in a cgroup, to manage the number of processes in a cgroup. Inside there is a hierarchy of directories, and each directory contains files for PID management. And if you don't know if you're on v1 or v2, a very easy way to tell is do ls sysfs cgroup, and if you see CPU, memory, and so on and so forth, then you are almost certainly on this legacy v1. So a concrete look at how it looks in cgroup 1. So you mount at sysfs cgroup. Inside you have this directory resource. Each resource manages its own distinct hierarchy. You can have a single PID, which is in B in PIDs, but also in A in memory or block I/O. And importantly, even though you use something like systemd and they all have the same name and they're all called something.service, we can't make any decisions because we don't know for sure that those only contain the same PIDs, right? We don't know that that's one unit of work. It's totally possible that you can mix and match PIDs in different cgroups in different resource hierarchies. By contrast, in cgroup v2, we don't see the resources at sysfs cgroup anymore, right? We see the directories for these systemd units themselves, things like async.slice or foo.mount and so on and so forth. So how then do we know which resources a particular cgroup has available to it? So in cgroup v2, the way this works is completely inverted. So now cgroups are not created in the context of a particular resource, but we instead enable or disable a resource in the context of a particular part of the cgroup hierarchy. So this means you, for example, opt into the CPU controller somewhere in this hierarchy, and then we give you files related to CPU control. So why wasn't what we had in cgroup v1 enough? Well, let's look a little bit at how cgroup v2 is designed and illustrate some of the issues it solves, right? So in cgroup version 2, we now have this unified hierarchy, which means cgroups are global. There is one cgroup for each process, and it shares that cgroup for all resources, memory, I/O, CPU, and so on and so forth. So instead of having a cgroup per resource, you have resources per cgroup. The idea here is that you or your container or init system opt into some subset of controllers using this cgroup.subtree control file, and you write plus memory or plus CPU, and voila, you get the files related to managing that in that particular cgroup. This might seem like a purely aesthetic change, going as a kind of an inversion of the hierarchy, but this actually has quite significant technical advantages. Without this major API change, we simply cannot use cgroups to do complex resource control, and resource control becomes quite unreliable when you actually go to use it. Take the following scenario. Memory starts to run out on your machine. When we start to run out of memory on a machine, what do we actually need to do? We need to go and try and free some up in order to try and make it usable again. So we will start reclaiming stuff like page caches, and we start swapping, which results in disk I/O. If we are particularly memory bound, or the disk is very slow, then this means we're probably going to spend a lot of time doing CPU work in order to try and do this freeing. In which case, now we're going to take non-trivial amount of CPU cycles in order to do that. So on some highly loaded or memory-bound workloads, it can even take in kind of the double-digit percentages of CPU utilization in order just to do this work when you're right at the edge of the machine. So when we have this multiple resource hierarchies, one-page resource, this actually becomes impossible to manage. It isn't possible to manage these transfers of resources between things. For example, in version 1, we cannot stop a cgroup from taking all of the machine I/O if you just limit the memory, which is exactly what's going to happen, right? Because we are just going to put it into essentially a very tight coffin by which it just uses the I/O constantly and thrashes the disk. So without this API change, effective resource control in a highly contended system is actually not really possible, which is why we've had to reinvent some parts of how Linux resource management work from the ground up in order to try and make things scale. So when I talk about reinventing things from the ground up, let's take a little look at memory, for example, because I think that's one of the things people commonly want to limit. One thing which is really critical to understanding Linux memory management is that Linux has different types of memory. From the CPU's perspective, there's not much difference. It does have some concept of, like permissions and things like that, but it doesn't really know, what is this page for. It doesn't really know what is this memory for necessarily. Linux does, though, and for example, anonymous memory, as the name would imply, not backed by any kind of named backing store. Memory explicitly allocated during the program lifecycle by something like malloc or by map anonymous is typically, this is all kind of anonymous memory. Most people also know about caches and buffers, kind of two sides of the same coin in Linux for a lot of years. They've been managed basically in the same way. But if you ask most Linux admins about caches and buffers, they will say that these two things are reclaimable. And I'm sure that's probably what most of you would say. But the problem here is that people have the wrong idea about what reclaimable means. Reclaimable doesn't mean that you can reclaim it. It means, if you ask nicely and at the right time, I might let you reclaim it. Which is slightly different because it doesn't necessarily manifest as something which you can use. It's not memory which just necessarily can be trivially freed. For example, if some application is hammering on some file constantly, it's very unlikely that we're going to be able to drop it from the cache, right? So while these caches and buffers can, under some circumstances, be freed trivially, it doesn't always have to be the case. And in some applications, it can actually be very, very large amounts of memory which cannot be reclaimed from these. This can cause some confusion when people inevitably ask, why did my application the entire machine when I had a bunch of caches available? But we'll come back to some of these more unexpected foibles around that in a little bit. The fact that caches can be essential is also an example of why RSS, or the resident set size, a metric that we love to measure as an industry, is really kind of bullshit. RSS skews a huge amount of attention towards a very few select types of memory, anonymous memory and mapped file memory. We forget, though, again, that many workloads simply cannot make any forward progress unless they have these extensive caches and buffers, or other kind of system-wide shared memory. The reason that we measure RSS, I would like to posit, as an industry, is not because it measures anything actually useful, but because it's really bloody easy to measure, which is a pretty nonsensical reason to measure anything. So when somebody asks how much memory your application actually uses, the only reasonable answer, unless you've compressed it until performance is degraded and you kind of know where that threshold is that you have no clue whatsoever how much memory your application actually uses. In one case inside Meta, which we'll come back to in a little bit as well, a team that had for years believed that they are using across the fleet on every single machine 100 to 150 megabytes, discovered through some of the technologies which we'll go over in this talk that they actually use a footprint of about 2 gigabytes of memory, which is quite a thing to discover after several years of running it in prod. So this is one reason why in modern resource control we typically limit all of the types of memory together, right? We don't selectively limit the caches or selectively limit anonymous memory. We just say this is how much memory you get and all of it has to fit inside this one block. Because if you just limited anonymous memory and, for example, ignored the page cache, you're still going to trivially allow one application to just kill the performance of all the others. So in cgroup 2, we account for all types of memory together, and we limit all types of memory together. That's why we have, for example, this memory.max file, not like the old days in cgroup 1 where you would have, memory.anonymous limit in bytes. You don't have a separate one. You just have, this is the amount of memory this cgroup can use, and that's it. You don't get to select which types of memory. This is a step change from, the per kind of memory type limits that were in cgroup 1. And on the surface, this looks like it should work pretty well, and it does. It does exactly what it says on the tin. It sets a maximal amount of memory which is allowed to be consumed by this cgroup. But the problem here is how to use this to compose a reliable system. So let's say that you have a couple of slices. For those of you who use systemd, this is basically terminology for some grouping of applications, some kind of class of application usually. So best effort ones in besteffort.slice would be things like configuration management or metric collection. Things that you'd really like to have running because you do need those things to run, but if the entire machine is unable to operate at the current time, we can kind of just not do that for 5 minutes. That's not really a problem. The workload, on the other hand, consists of the applications which you must serve on this machine. For example, it might be HHVM, Nginx, something like that on a web server, or MySQL on a database server. And you might, of course, have many workloads on the same machine in kind of a stacking scenario, but for now, just let's look at one for simplicity. So the typical administrator, the typical system administrator, trying to be very responsible, might have a way of thinking that goes something like this. I am now scared that non-critical applications might kill things, so I'm going to put them in besteffort.slice, and I'm going to set memory.max on it. Oh, but now I'm worried that I've put too many things inside besteffort.slice, and one of them is much more poorly behaved than every other one, so I'm going to set memory.max on that one as well, so it doesn't affect all the others. And now I'm worried that, my workload actually should only grow to a particular size, so I'm also going to set memory.max on that as well. And so on, and so on, and so on, and so on, until you have a system that I don't know how the hell you're supposed to reason about it, because every single limit is operating independently, and the moment that any of these application requirements change, the whole thing falls apart. If you go one page over, it's going to be game over for you. So our ultimate goal here is just to keep whatever's in workload.slice running, right? So why are we setting all these limits? All we want to do is keep workload.slice running. What if we could encode that? What if we could just write this instead? So as opposed to memory.max, memory.low is a fundamental change to the way in which we've gone about apportioning memory on Linux and Unix for the past kind of 50 years. The idea is that instead of trying to control memory for each application, we instead bias memory work towards certain other kinds of places. For example, in this case, what we're doing is essentially saying workload.slice needs 20 gigabytes to operate, and I expect it to need 20 gigabytes to operate, and as long as it stays within those confines, I will prioritize other things to have memory taken away from it instead of this. But how does that actually work? So all of this works based on reclaim. Reclaim is a fancy name for this kind of process of trying to free pages. This kind of freeing might either work based on a global memory shortage, where you're kind of brushing up against the limits of your system, or it could be brushing up against the limits within something like a cgroup, right, and then trying to get back down again. Memory.low hooks into the kernel's reclaim infrastructure in order to do what we would call protecting some memory for a cgroup. For example, if you have, as in the previous example, memory.low equals 20G, as long as that cgroup is below 20 gigabytes of use, you'll generally be exempt from having memory taken away from you. This means that we tend to reclaim any memory that the system needs to make forward progress from everywhere else except for you. The only time which will dip into your memory.low reservation is if there's an immediate global memory shortage which we cannot resolve otherwise. And you'll see when that happens because we have a kind of statistic file in each cgroup which says when we are reclaiming, even though we know you're within your protection threshold. This might sound kind of simple, but in reality it's pretty non-trivial to implement because this is almost completely the opposite of the way we've thought about controlling memory on Unix for a very long time. For example, if multiple protections are competing against each other, if you have multiple cgroups with memory.low set, we have to decide how we should prioritize those protections. We also have to do things like how to decide when you have one cgroup with a protection and has a lot of children, how should those children get a portion of the protection? How should they compete for the protection? We also need to handle the case where you're slightly over the protection, which is not that abnormal, and try and work out some scheme by which we do reclaim from you, but not as much, because you are not that badly behaved. If you have 20 gigabytes of protection and you're using 20.1 gigabytes, we don't want to treat you as a poorly behaved entity, right? You were just kind of doing your thing and you're slightly over the protection. So that's one thing we also need to work out. Another nice effect of this is that compared to memory max, this is far more work conserving. Work conserving is this fancy term which is now coming back into vogue. It essentially means as long as you are not affecting the system from making forward progress, you can use as much memory as you like. We don't limit you to 20 gigabytes. You can use as much memory as you like with memory.low. The only thing we are doing is apportioning some amount of memory which we want to kind of prioritize you for. We are not limiting you to 20 gigabytes. So this is much more tolerant of these temporary spikes and changes in memory composition. And we now primarily rely on memory.low instead of memory limits in production at Meta. There are still some kind of niche use cases for limits, so we do use them in places, but at the fleet level, we've mostly transitioned to using memory protections instead of memory limits. So since we're talking about memory, here's a nice, easy question for everyone in the room. I think they know what's coming. How do you view memory usage for a process in Linux? I have many answers, many answers to select from. So at the front, I think I heard PS, right? So the thing about PS, the thing about PS is that it really only kind of measures like one type of memory, right? It does know something about caches and buffers, but it highly incentivizes you towards either looking at the virtual set size, which kind of doesn't really make much sense, or the resident set size. And the reason is because historically, caches are like this big shared resource in which we don't really know who is doing what, but you all just kind of use it, and hopefully everyone will be happy and everything will be great. You might be thinking, caches are just optional in this case, but the problem is, as we kind of went over in the example, with this kind of 2 gigabyte working set, it's not really true in some cases. In a lot of complex applications, you have quite a large amount of caches you need to actually sustain workload performance. Let's take Chrome, just as a completely facile example. The Chrome binaries code segment is over 130 megabytes. He's a big boy, he's a big one. But we load this code into memory as part of the page cache. We can't just, kind of sign that off and say, somebody else will sort it. We actually need to have those code pages in the page cache. Otherwise, we cannot execute anything. So this is kind of an example of why we need presence of caches in main memory, and sometimes you can't just evict them. The same goes for things like caches for files which are explicitly loading. Eventually, those pages do have to make their way to main memory, and we can't just evict those. We do actually need them to do things. We went over this egregious case from earlier of like the team which thought they were using 100 to 150 megabytes, and they ended up actually using 2 gigabytes. That daemon in particular, what it does, and I think a lot of us at large companies have a daemon like this, it aggregates metrics across a machine and it sends them to some kind of centralized graphing storage, right? So as part of this process, it runs a bunch of arbitrarily defined scripts in order to try and get data. And for years, the team writing and maintaining this daemon thought it was about 100 to 150 megabytes. But with this 2 gigabytes, the thing about that is it's essential memory. It's not 2 gigabytes and it runs well. It's 2 gigabytes or it doesn't run at all. And it's just going to grind to a halt. And almost all of that memory is locked away in caches. Actually, the anonymous portion is so small compared to the whole thing. So it really shows that caches are not always optional for forward progress. So in cgroup 2, we have this file called memory.current. And what it does is measure the current memory usage for the cgroup, including everything, including the caches, the buffers, and so on. So, job done, right? Surely that's the end. Well, the problem really here is that when people come to cgroup 2, and I give a big lecture about don't use RSS, it's bad, okay, they don't really, they just go to memory.current, and they say, You have a new metric, I'm going to use your one because clearly it's the right one. The thing is, memory.current is a file that, as you might guess, contains the current amount of memory used. But it's quite important to understand what that means. The very fact that we're not talking about the current RSS, but the actual memory usage in the cgroup, means the ramifications are very, very different, right? Caches, buffers, socket memory, kernel objects which we allocate for a process, all of these things are contained in there. And that's exactly how it should be, because otherwise we would just be able to trample over other parts of the system which do need to make use of that memory. So understanding why, reasoning about memory.current and not just using it as a replacement for RSS directly is something to do with why we gravitated towards metrics like RSS in the first place. The reason people chose RSS is because it's relatively static, right? It's not necessarily very useful, but it makes you feel good at night when the graph doesn't move, and you say, job done, I've done the memory is done, completed it, mate, and that's done. So the problem here is memory.current suffers from completely the opposite problem, in that it tells you the truth, and people don't really know how to deal with that. For example, if you set an 8 GB memory limit with memory.max, I'm aware I've told you not to do that, but let's pretend that we're doing that for now. If you set an 8 GB memory limit with memory.max, what's going to happen? And if there's no system-wide memory pressure and we let your application run for a few hours or something like that, what is memory.current going to be? It's probably going to be 8 GB as well. And that's not because your application needs 8 GB to run. It's going to be 8 GB because there's no reason for it to shrink it, right? We are putting buffers and caches, we have slabs, we have kernel objects, we have all kinds of things which nice to have stuff that we don't really necessarily need, but it's nice to have and there's no reason to get rid of it, so why should I get rid of it? So it's just going to grow to the size that you've set as the limit, right? It's not that your application really needs it, but if there's no pressure to shrink, then there's no reason to do so. So what should we do? How should we know what the real amount of memory that your application needs is at any given time? So to answer this question, we need the assistance of another technology which has been invented at Meta. So let me ask you another question, because the first one went so well. Let me ask you another question. How can you tell that you are running out of physical memory before you run out of physical memory? I think somebody said trick question. Of course it's not. I didn't trick you the first time. I'm a very honest guy. Oh, I've scared you all, haven't I? Jesus. This guy's just throwing himself on the grenade, on the grenade for you. I rate it. So top or free or something like that is usually the answer, right? The problem there is on all of these systems, the goal is pretty much always to run with all your memory full, right? Your goal is to always run with all your memory used. It's not to like shrink it to the minimum size, but you want to make as much use of it. This is one of the big misconceptions about efficiency, right? Our goal is to make the most efficient use of resources on the system. That doesn't mean using nothing. That doesn't mean shrinking it to nothing. It means making the most out of everything that we have, including the memory, to do things like caches, buffers, and so on and so forth. So the problem there is that it doesn't necessarily imply being saturated. Being full might be a good state. The same is true even for this kind of more correct, like we regret ever putting this in the kernel, I would tell you. We have a metric called memAvailable in proc meminfo. The amount of regret we have about putting that in the kernel is immeasurable, and we would like to retract it from history if possible. So the problem there is like that is a very convenient lie. It is, however, a lie, and it also promised not to be a lie when it called itself memAvailable. So let's pretend that doesn't exist. Another metric which people who are kind of maybe a little bit more senior might mention is something like page scans, which is the rate at which we are iterating, trying to free pages. We're trying to find something to reclaim. And the problem with page scanning is that it's really hard to differentiate the page scan rate when you are kind of making very efficient use of the system. You are just kind of turning over pages and you're making good forward progress, and when you are now at the point where you really can't make any forward progress and the system is about to fall over and die. If your page counts are high, it could mean kind of either. So it's not really hard, it's not really easy to tell based on these which of these is going to happen in the next few seconds. So usually all metrics that we come up with are an approximation for memory pressure. So what is memory pressure? So we've never really had a metric for this in the kernel before. We have all these related metrics, like the ones we discussed around kind of free, the stuff shown in free on top and meminfo and so on and so forth. But it's hard to tell what real pressure is from efficient use of the system with those, right? So PSI, or pressure stall information, this new technology which uses these metrics specific to a resource to determine, is this resource oversubscribed, and if so, by how much is it oversubscribed? So for example, in memory, we use the amount of time in which threads on the system were stuck doing what we would term non-essential memory work. So some here means some of the threads were stuck doing memory work which we deemed not to be essential for 0.21% of the time, for example, in the last 10 seconds. Full is exactly the same, but it means all of the threads in this C group were blocked. This could be things like waiting for a kernel memory lock. It could be things like being throttled. It could be things like waiting for reclaim to finish. Even more than that, it could be kind of refault or memory-related I/O, which can really dominate, like having to page fault file content into the page cache over and over and over again because you are kind of exceeding the amount of memory which is available on the system. Pressure is essentially saying, if I had more of this resource, I could have ran 0.21% faster in the last 10 seconds. This can also be really useful to you in developing these kind of high reliability and high availability applications. For example, we use this in advance to know when we are going to use too much memory probably and do load shedding. We use it as part of our kind of background async tier to know when we should back off some request because we are already kind of close to the bounds, right? We also use it for our user space pre-UM detector, UMD, which is now kind of graduated into a systemd project, systemd UMD. And that has kind of a fine-grained policy engine about where you can encode what would I like to do if memory on the system becomes really scarce. And it uses PSI as the backend to determine that. We use it for all sorts of things elsewhere as well. We not only at Meta, but in terms of Google, we also use it for Android. We've been working quite a lot with Google people on using it for resource contention detection on phones. And you can't just get this by like looking at free or PS or something like that, because you don't really know, is this oversubscribed or is this an efficient use of the system? So coming back to what I mentioned about memory.current, right? Like, how does this relate to the case that I mentioned earlier, where we have all this slack in memory.current, and we don't really know the actual amount of memory that our application needs to execute? So let's take an example kernel build, which with no limits and 4 threads for builds, has a peak memory.current of just over 800 megabytes. So in cgroup v2, we have this tunable called memory.high, which will reclaim from the cgroup until it goes back under some threshold, or it will throttle the cgroup and stop it from executing. So right now, things take about 4 minutes to build with no limits. When we apply a memory threshold of 600 megabytes, bearing in mind that without any limit it's 800, when we apply the 600 megabytes, actually the job finishes in about the same amount of time, with about 25% less available memory. It's still 4 minutes, just about a second or so more in wall time, so pretty good trade-off. The same even happens when we go down to 400 megabytes. We're now using half the memory that we originally used, with only a few seconds more wall time. However, if we dial it down just a little bit further, things never even complete. We are now 9 minutes in and it's not done, right? We've gone down 100 megabytes to 300 megabytes and we have to control-C it because the build will just never complete. So we know that this build job needs somewhere between 300 to 400 megabytes of memory to operate with reasonable performance and make reasonable forward progress. Finding the exact cutoff where the job performance begins to plummet is a very tedious trial and error process. And this trial and error process also only works for something like this, where you do the same work every single time. But it doesn't work very well, for example, for a web server, where you might get more requests or less requests, and you need to adapt to that, right? So to get an accurate number for services at scale that have highly variable memory usage, we need a better and automated way. So determining this what we would term the working set size, or which is basically the memory required for a particular application or service, is a very difficult and error-prone task. So Senpai is this self-contained tool that uses cgroup v2's new pressure stall information system to find out how much memory does it actually need. How much does a kernel build job, in this case, actually need to do its job? So the way it works is that using PSI and memory.high, PSI to tell how much pressure is being exerted, and memory.high to exert some pressure, Senpai applies just enough memory pressure to evict cold memory pages which aren't necessary to maintain forward progress on the workload. It's an integral controller which dynamically adapts to these memory kind of peaks and troughs. So when you get more requests, we expand the memory.high, and when you get fewer requests, we contract it. An example case being something like a web server, when more requests come in, then you can shrink and expand as needed. So it essentially provides this memory working set profile of an application over time. So it can be used to answer this question we posed earlier, which is how much memory does my application need to run? And in this case, for this job, we find out the answer is actually about 340 megabytes or so. And to get there, we keep pushing until we start to see pressure using memory.high, and then we adjust as necessary to keep it just tight enough without invoking, like an anemic power in its component. So what are the benefits of this shrinking? You might be sitting here thinking, like, why would you want to do this? Because, it's just going to make the best use of the resources anyway as the kernel. So as I mentioned, first of all, we had this example from earlier of the team that had no idea how much memory their application is actually using, right? So this is how we managed to determine that the actual needed amount of memory for that service is 2 gigabytes and not 150 megabytes. So we use Senpai internally to find these regressions and leaks in a way which you cannot do with RSS measurement because there are plenty of other ways to do it other than just anonymous memory. Another thing that we use Senpai for is to get ahead of memory shortages and amortize the work to try and avoid them ahead of time. So when a machine is already very heavily contended, like you're using a lot of the CPU and you're using almost all the memory, it might be very hard to free some memory just because it's hard to ask to do anything else right now. Like we are already basically smashing the system to pieces, like we are asking it to do a lot already, so I can't really free up that memory. So if we can amortize that work ahead of time, keep things as small as they need to be in order to continue operating with nominal performance, then we don't have to do that when the machine is already highly oversubscribed. So the combination of these things means that Senpai is an essential part of how we do, for example, stacking, workload stacking at Meta. It not only gives us an accurate read on what the workload needs are right now, which means we can choose what to stack with it, but it also allows us to monitor over time and adjust the stacking as necessary. This feeds into another of our efforts around efficiency, which is memory offloading. So traditionally, on most operating systems, you really have one memory offloading location, and that's it, which is your disk, right, with swap. Even if you don't have swap, it's still true, actually, because of things like demand paging and the page cache, where you do have to read from the disk. You still have to do I/O, even if you don't have swap. But there are a lot of granular, kind of intermediate levels, right, which we could use for page offloading, possibly. When we talk about offloading, this means that, yes, we are going to have to do a page fault in order to get it back into main memory and do something with it, but getting that data back into main memory may be much easier or much harder for some of these offloading locations than they are others. For example, it's going to be a lot easier to page fault in from an SSD than it is from a hard disk because it tends to involve random reads doing swaps in. Hard drives are pretty slow in general, but they are particularly bad at doing head seeking for random reads. But there are also more granular things that we can do as well. For example, one thing we can do is to start looking at strategy outside of the hardware. One of the problems of the kind of duality of either being in RAM or being on the disk is that even though SSDs are not that slow, they are a lot slower than main memory by several orders of magnitude. But many workloads have what we would probably term warm memory, which is not memory which is necessarily needed all the time, and not memory which is cold enough that we can just swap it out and never see it again, but things which we need relatively infrequently, which if we had an easy way to just kind of amortize some of the work there, it would be nice. Like, it would be nice to get it out of main memory for a little while. So one area which we've been heavily invested in is improving and productionizing ZSwap, which transparently compresses these kind of warm but not hot pages. So ZSwap compresses pages that look like they will compress well and are not too hot into a separate pool which is still in main memory. In order to use those pages, you do have to page fault them back in, of course. You can't just use them in their compressed form, but this is usually pretty cheap and fast, and importantly, it doesn't require any disk I/O to do, unlike swap. We still do have disk swap, so you end up with this kind of tiered memory model of hot pages in main memory, warm pages in ZSwap, and cold pages on disk swap. So this kind of provides this tiered hierarchy where, of where to put pages which aren't mandatory depending on how soon we expect them to become mandatory. One problem we've had here is that even when we configured the kernel to swap as aggressively as possible, it still wouldn't do it, which is funny because if you read on most people's articles about swap, they're always complaining it always swaps. But really, if you've looked at that code and I've had the horror of working on the damn thing, then you will know that this swap algorithm was largely implemented a very, very long time ago by the blessed elders who knew what to do, and they are not around to be asked what on earth this heuristic means anymore. So, I can't even describe to you really how the old swap code works because there are a lot of heuristics there and not a lot of detail about why things are necessarily the way they were. The answer for a lot of them is because they were only really rotational disks, right? That was where you put swap. and rotational disk and swap don't really work very well. But now, we have to think about how to make this work for the modern era. We have non-rotational disks, we have flash disks, we have Z-swap, which is not even on a disk, and we have SSDs. We want to make more efficient use of swap on these mediums for swap and build an algorithm which can deal with this better. So for this reason, even with swappiness set to 100 in those old kernels, the kernel is historically very, very conservative about actually swapping. So in the recent kernels, we've been working on making the swap algorithm a little bit more willing to do it if it seems like a good idea. The new algorithm works something like this. So first, we now have code to track all swap-ins and cache misses across the system. So for every cache page, which we're having to page fault and evict, and page fault and evict, and page fault and evict because of memory pressure, try and swap out a heap page instead. If we're unlucky, and this heap page actually ends up being kind of hot and pages right back in, no worries, we'll choose a different one next time, and hopefully we'll make some better forward progress. However, if we are lucky, and the heap page stays swapped out, that's one more page which we can use for caches or for other processors' memory. This means that we can typically engage swap a lot more readily now in most scenarios compared to all the different constraints we had previously. Importantly, though, we are not adding I/O load here. This is not a trade for more I/O load. We are just more intentional in how we apply the existing I/O load. We are trading one paging for another type of paging. And our goal here is to reach an optimal state where the optimal state is actually doing the least amount of I/O which is necessary in order to sustain workload performance. And ideally, we use this kind of tiered model of memory management where you have the thing which I mentioned earlier, like the hot page, warm page, and cold page in different places in order to do that. So this is a super simple idea compared to the old model. The old algorithm does have a lot of quite complicated reason about heuristics, all kinds of penalties, a lot of conservatism due to the cost of random reads on old disks, and that did make sense at the time it was made for sure. But in general, it was not written for an era of devices like SSDs or in-memory swap. So what were the effects of this strategy change in prod? So on web servers, we not only observed an increase in performance, but also a reduction in heap memory by about 2 gigabytes or so out of about 16 gigabytes at total. So that's a huge amount to reduce by. The cache also grew to fill this newly freed space and grew by about 2 gigabytes, from about 2 gigabytes of cache to about 4 gigabytes of cache. And we also observed a measurable increase in web server performance from this change. So you don't usually get all of these things at the same time, right? Usually you're trading off between all these things. So it probably indicates we're doing the right thing. We are increasingly reclaiming the correct things where we weren't before. So also disk I/O was reduced because you don't actually have the amount of disk I/O required anymore because we don't have to continue page faulting and evicting and page faulting and evicting. This also meant on some workloads now we had the opportunities to stack workloads where we previously couldn't do that. Many machines don't use up all their resources, but they use up just enough that it's hard to run a second workload there. So this is another cool thing which we can now potentially do on tiers where we previously had just been kind of over the edge on memory, where we couldn't stack. This combination of changes to the swap algorithm using Z-swap and squeezing workloads using Senpai was a huge part of our continued operation during COVID. All of these things together we term TMO, or transparent memory offload, and you can see some of the results we had in production over here. In some cases, we were able to save up to 20% of some fleet-wide workloads memory with either neutral or in some cases even positive effects on performance. So this opens up huge opportunities in terms of reliability and stacking and future growth, which were things we really needed during COVID especially. This whole topic could be a talk in itself, so I've given a link at the bottom. If you want to learn more, my colleagues Johannes and Dan wrote an article with even more depth on how we achieved what we achieved. So let's come back to this slide from earlier. We briefly touched on the fact that if bounded, one resource can often trivially turn into another one. A particularly egregious case there is memory turning into I/O when it gets limited. But for this reason, we need to always have controls on I/O when we have controls on memory. Otherwise, memory pressure will just translate directly into disk I/O. Probably the most jejune way to solve that is to try to limit the disk bandwidth, IOPS, which looks probably familiar to those who have done resource control in the past. However, this doesn't usually manifest very well in reality. If you think about any modern storage device, they are often a queued device. You can throw a lot of commands at it, and when you throw a lot of commands at it, it turns out magically, internally, it can do more stuff. It's hard to really work out how much it can do, and when you're actually at 100% memory usage, 100% I/O saturation. The mixture of I/O also really matters, even on SSDs. Things like reads versus writes, random versus sequential reads. It's kind of hard to determine really a metric for loadedness for storage devices. If you have a dashboard which shows like disk utilization, what does it usually show? Well, it shows you another very convenient lie, which is similar to RSS, which is how much wall time was spent doing disk work. But it does not tell you whether you could have done more disk work, because even if you're at 100%, it may well have been able to do more disk work. This is also really punitive. If nobody else is using the disk, you still have a fixed limit which you can never exceed. And why would we want that? We wouldn't want that if the disk is otherwise not being used, right? So it's not really great for this kind of best effort work on machines with highly variable loads. So the first way in which we tried to solve this problem is by using latency as a metric for workload health. So what we might do is apply a maximal target latency for I/O completions on the main workload, and if we exceed that, we start to dial back other cgroups with looser latency requirements back to their own configured thresholds, and so on and so forth. So what this does is it prevents an application from thrashing on memory so hard that it just kills I/O across the entire system. This actually works really well if you only have one workload, but it doesn't work very well in kind of the multi-workload case like this. So here you have two high-priority workloads which are stacked on a single machine. One has an I/O.latency of 10 milliseconds, and the other one has 30 milliseconds. But the problem here is, as soon as workload 1 gets into trouble, everyone else is just going to get throttled, right? And there's no guarantee that the other things are the thing actually causing the problem, so why would I want to do that? This is kind of fine if the thing which you are throttling is something which is best effort, which you don't really need to run. But here we have two high priority workloads, so I'd really rather not do that. So I/O.latency is great if you only have one workload, but it's not really possible to prioritize multiple stack workloads with it, because any not highest priority application ends up being tends to be throttled too harshly. So how can we solve this? So our solution is this thing called I/O.cost. So it might look very similar at first, but notice that now we have no units on any of these tunables, right? These are not units in milliseconds, but a cost-based solution where you specify some weight for the cgroup. So how do we know what 40, 100, or 60 means in this context? Well, the sum of all three is 200, and if that's the amount you have across the system, best effort.slice should get about 20% of saturation capacity, workload 1 should get about 50% of saturation capacity, and workload 2 should get about 30% of saturation capacity, because that's how much it adds up to relatively. Just like I/O latency, this is work conserving, which means that if nobody is using the disk, any one of these is free to use the entire disk, the entire saturation capacity of the disk. But this is not that simple, right? We went over that, you can throw a lot of commands at them, and sometimes you discover that more things can be done. So how do we know when we've reached the 100% saturation of the disk? How do we know when that's actually happened? So the way that I/O.cost works is it builds a linear model of your disk over time passively by looking at the I/O which is being performed. So it sees how the disk is responding to variable loads, and it builds a model based on things like, is it a read or a write I/O? Is it a random or sequential I/O? What's the size of the I/O? What's the state of the overall system? And using all of these things, it builds an idea of what the saturation capacity of the disk looks like and what influences it towards saturation. So it boils down this quite complex operation of how much latency or throughput does my application need to a simple weight-based prioritization system, which is much more similar to how we do, for example, CPU scheduling. It doesn't suffer from the same problem as I/O latency with multiple workloads, since you can stack workloads with it, because it doesn't penalize others. There's no penalty for others if you go over. It's just that once the disk reaches saturation, we have a clear prioritization between the three. The basic on-the-fly model, if you don't do any configuration other than this, uses queue depth as the back-off mechanism. It uses that to determine disk saturation, which works okay in most cases, but if you want more fine-grained control, we have this link at the bottom right, res cuddle bench or resource control bench, which builds a model of your disk. It does very fine-grained injection of I/O into your disk, and because we can control things very, very tightly, it can build this model much more efficiently. But the default model does it passively as your computer is running. This is a bit more accurate. This kind of tuned model is more accurate because obviously we are much more able to tightly control the parameters which we are injecting. But whether you use the on-the-fly model or the quality of service model, the weight system in general simplifies the balancing because you don't end up thinking, like how many milliseconds of latency am I willing to tolerate or something like that. In the old days, when I went to conferences and talked about cgroup v2, the historical response was, that's nice, Docker doesn't support it, so this was a waste of time. which was fair. I can see Phil nodding. Yeah, like nowadays things are a lot better, right? We spend a lot of time working with people at Docker and in other places to work out how this should look for their model. They often have quite a specific containerization model and want to know exactly how this should fit into it. So we spend a lot of time working with them, and in general, pretty much everything that you would use supports it. We're also really thankful to Fedora for making cgroup v2 the default since Fedora 32, as well as making things a lot more reliable behind the scenes for users. This really was like a kick in the arse for everyone else who had no cgroup v2 support, because the entirety of the Fedora forums were filled with, now Docker doesn't work, please help. So it was a good signal that if you're serious about containerization, you probably should actually consider supporting cgroup v2, and now we are at a much better state than we used to be. Even if your distribution doesn't boot with cgroup v2 by default yet, you can boot it yourself by specifying cgroup no v1 equals all on the kernel command line. The v1 controllers, as you probably guessed from the entirety of this talk, are backwards incompatible for very good reason. So this makes sure that your system only boots with v2 support, and things like systemd will automatically pick it up and use it. The KDE and GNOME folks have also been using cgroups to better manage their desktop handling. David Edmondson and Henry Chain from KDE in particular recently gave a talk at KDE Academy. Their talk was entitled, "Using cgroups to Make Everything Amazing." Now, I'm not brazen enough to call my talk that, but I won't disagree with it. It basically goes over their use of cgroups, and in particular cgroup v2 for resource control and interactive desktop responsiveness. This is definitely kind of a developing space, because as you can imagine, we have largely been concerned about the server use case, but nowadays most of the major desktop environments are investing here in using cgroup, and in particular cgroup v2, to help the desktop experience. If you're interested in that, I highly recommend watching their talk from the link at the bottom. It really goes into the challenges they've had and some of the future things that they want to do, and how cgroup v2 will help them with that. Android is also using the metrics exported by the PSI project to detect and prevent memory pressure events that affect the user experience. On an interactive surface like Android, latency is absolutely critical. It would really suck if you went to a website and you click a button and now you need one more page, and that page is not available, and you just, the whole phone just freezes. That's not exactly what you want. So we've been working with engineers from Google on using these pressure metrics we've created to more proactively prevent these scenarios and produce a more kind of responsive and reliable experience. So hopefully this talk gave you some ideas about some of the things that you might want to try for yourself. We're still very actively improving and developing kernel resource control, and your feedback is one of the things that we definitely need to help make it a success. Obviously, everyone's needs are quite different, everyone's organizations are quite different, everyone's containerization strategies are quite different. So we're really eager to know what we could be doing to help you out and help you with your workloads and services in particular. I'll be around after the talk. I don't think there's anything immediately after me, so I'm more than happy to chat. But feel free to also drop me an email or message me on Mastodon. More than happy to hear any of your feedback and suggestions. I've been Chris Down, and this has been 7 years of cgroup v2, the future of Linux resource control. Thank you very much. Yeah. That's fine.
Make sure I get to the question or repeat the question.
Sure thing, I can repeat it, that's fine.
Questions? Great talk, Chris. I've been following the V1 versus V2 debate on the forums, and do you know any reason why it has not been enabled by default? Is it because of the process versus the thread discussion that they've been having?
Sorry, I think I missed the beginning of your question.
I was following the V1 versus V2 debate for a very long time. They were not enabling.
Do you want to try that again?
Okay.
Immediately that you said that, somebody was loud again.
Sure. This is the third time. Third time is charm.
Well, third time's a charm. 3 is the magic number, as Della Sol once
The
said.
V1 versus V2 debate that been going back and forth between the maintainers, is it one of the reasons why it has not been turned on by default?
So the question is about about V1 versus V2. Why isn't V2 the default? I guess. So this is basically over because all the people working on cgroups do not work on V1. In fact, when patches come in for V1, we don't accept them. We just write back, we don't support V1 anymore. So it's basically a solved problem right now. The reason we still boot with V1 is because there is still, obviously there are a lot of kind of legacy concerns, especially if you're booting with some old container. Imagine you boot with a very old version of Docker on a new kernel. We're not really at the point where there's been enough years to say, like, I don't really care about those, or where Linus is willing to say, like, I don't really care about those anymore, where the practical concerns are low. Mostly now, the impetus is on the distributions, right? So Fedora has now put it as the default. Most of this is going to be enabled through the distributions. I mean, we have the same thing with a lot of other things in kernel, right? If you've ever gone through like make menu config in the Linux kernel, you've probably seen almost everything says, if you're unsure, put n, and it'll be something like, you have a screen. Yes, I do actually want that, it turns out. So that's pretty much the level of like conservatism we're talking about here. So, but it is pretty much sorted. Like, there is no reason to not use cgroup 2 now. In the old days, one of the reasons was like the thread versus process thing. That was mostly for the CPU controller, but now that's merged, and that's not really a thing anymore.
Hi. Yeah, it was an interesting talk. I found an issue on the Flatpak bug tracker about setting limits on Flatpak applications, and it says that it's not possible right now with cgroups v2 because it's unprivileged. You know, it's not a root user that's running the app. Do you have any ideas on if that will be possible at some point?
Oh, that is possible. I don't know. Do you wanna just come and sum of the issue afterwards, and I'll write that it is possible.
All right.
Mission complete, innit?
Right.
Yeah. So yeah. I mean, we have the normal. So all of cgroups work through kernelfs. In that you can set your own permission model. Maybe there is something specific they are doing, which they have a very specific way of doing it. But actually, I don't think anything really changed between v1 and v2 for the permission model. So, but I assume that if somebody's written that, then the answer is that just their existing model of how to do it is not feasible for some reason. But I can take a look if you send me the link.
Okay. So a non-root user should be able to set limits on the.
Not by default, but not by default in v1 either. You need to tell it that you know this is delegated to this particular user by chowning it, for example. So.
Hi, great talk. So I read from the author of systemd a while back that he was kind of lamenting that cgroup v2 isn't a proper job feature, so you can't kill an entire slice at once. So the way systemd handles that is it loops through in user space, reads the PIDs, and then kills them, and so there's race condition involved. And I was just wondering if that's part of the plan for cgroup v2 to handle that or make it more of a job control.
I like how you avoided saying Leonard's name as if it was Voldemort.
I'm not sure how to pronounce it.
The inventor of systemd. Yes, well, the inventor of systemd. So I mean, okay, so I can speak with some position of authority, I guess, since I'm also systemd maintainer. But so we have that. We already have that. We have memory.oom.group, which does that. When the main process dies, the whole thing just dies, and that's done in kernel. Yes, that was lamentable when it first came out, but we have it now. We still have the legacy code in the job manager in systemd because we still support kernels which don't have that feature, but it actually exists now. And I mean, in terms of like interaction with Leonard, like we as cgroup v2 team and systemd people, like those are almost the same people. Like we are. There's a lot of overlap between that, right?
So one of the problems with running out of memory is that applications on at least the Linux desktop don't really save state. There's no real way to communicate to save state. And people have tried Signals. There used to be session management, but no one really supports it anymore. What do you see for a future there? Is there anything the kernel can do to help, systemd could help, that we could actually have a world where, I mean, it's almost the Android experience, where my applications could shut down when I run out of memory?
Yeah, it's an interesting point. I think some of that comes down to the fact that when we invoke the killer, like in terms of the global there's no time to save state because we're just trying to yeet everything as quickly as possible, right? So that's one of the reasons why we moved to this kind of oomd model, or the systemd oomd model, where you proactively say things are starting to look pretty bad and maybe I should do something about that. So right now you do have the opportunity in systemd oomd and in oomd, which is the kind of progenitor of that, to set which signal am I going to send and when. Like, under what condition am I going to send sigterm? Under what condition am I going to send sigint? Under what condition am I going to send sigkill? And so, yes, in some sense you can have that. obviously this is not a solution for like the synchronization or like the storage of like the application state, but it at least opens the opportunity to have something which does take that, right? Because you are not at the stage where like the whole system is falling down and you have no opportunity to do anything. So I think some combination of UMD or systemd UMD plus, you know, having some shared framework for saving application state, I think that is probably somewhat the answer there. And to some extent, that's what Android's done, right? Like Android has like some shared idea about how to do that. Thank you. That's a good question.
Okay, thank you very much.
Thank you. Thank you, everyone, for coming.